Hello, so in this video we're going to look at sort of solving a non-homogeneous second order differential equation. Okay, so remember non-homogeneous is where this right hand side is not zero. Okay, and we're going to look at the case when the right hand side is going to be something involving an exponential. So if you remember kind of in the last video I talked through the basic method behind it, and at the end of the last video as well I also found the non-homogeneous solution, so in other words the complementary solution. Okay, remember we're seeking a solution to the, this will follow a solution by the method of undetermined coefficients, and it is the method of undetermined coefficients because these things are constant. The constants in front of there, coefficients in front of there are constants. Okay, and we're looking for a form where it's y complementary plus some particular solution. And in this video we're going to try and find what that particular solution is. So we found yc. Now we're going to try and find the particular solution. Okay. So basically what this is saying is we're trying to find a y, so we're trying to find y equals something, which when we plug it into here, okay, left hand side equals right hand side. So in other words, when we plug the function in here, the derivative of the function and the second derivative of the function, okay, we get the right hand side looking like this. We get left hand side equals right hand side. So that's basically what we're trying to find. Now, we're not just going to make a blind guess. So in other words, we're trying to find what that y is. Well, we're not just going to make a blind guess. Okay, we could make a blind guess if we wanted to, but likelihood is we'll be way off. Okay, so what we're going to do is we're going to look at the right hand side to give us a kind of clue of what it will look like. Because normally the right hand side will look something like at least one. Because remember, there could be millions of solutions. There could be millions of functions that will satisfy this. Okay, but normally the right hand side will look like at least one of those solutions. There may be others, but it will look at least like one. And remember, the whole idea behind method of undetermined coefficients is that we only want to find one. We only need to find one. We only need to find one particular solution. We don't need to find all of them. We just need to find one of them. And because we already have the complementary solution, therefore we can find the general solution. Okay, so that's the whole idea behind this. So basically, we're going to look at the right-hand side. Basically what we're saying then, I suppose, is that when we put a function, into this thing, and its derivatives as well, so the derivatives and the function on the left-hand side, okay, we will get something. What this is basically saying is that we'll get something, when we put the function in, we get something involving e to the power of 2t. Okay, the fact that it's 3 is kind of, it doesn't matter so much at the moment, but basically when we put this in, we'll get something involving 2t. Okay, so a pretty good guess for what our function is going to be, is going to be something that looks like e to the 2t. Looks like something to the e to the 2t because, we're going to have to take derivatives of it and so on and so on. So basically, the pretty good guess, basically what we're saying here is that when we put a function in and take the derivative of it, okay, because of course, the derivative of e to the power of some function is going to look something like e to the power of that function. So when we differentiate it, it's still going to look like e to the power of that function. What I'm basically saying then is that a good guess is to make our solution, make our function look something like e to the power of 2t. Okay. Now, some of you may be tempted to say, well, why don't we stick a 3 there? There's a 3 there, so why not just say that our solution is basically just going to be our right-hand side? I would really err on the side of caution for that. I mean, you could try it, and maybe you might be lucky and it might work, but in general it probably won't work because this 3 is probably a result of kind of adding and subtracting and multiplying. There's a -3 there, so it's probably -3 times something and then -4 times something, and then you add them all together and stuff. So this -3 is probably a result of sort of several other processes: multiplying, dividing, differentiating, etc. So just keep it general to be safe, and let's just call a general coefficient. There will be, keep a coefficient there because there's a coefficient in there. So keep a coefficient there, but just keep it general, just to be on the safe side. So let's just call it A. Okay. At the moment, we don't know what this is. Now, notice that we don't put a constant. You could equally make the same argument for up here. This power up here. Why not say, well, why don't we just let it equal e to the bt, for example? E to the bt. So why don't we try a solution like this? The only trouble with that is that kind of makes it look a little bit too general. It's a little bit too general because, of course, the whole idea, because if you differentiate a function, if you differentiate e to the power of some function, it's going to be f dash x, the derivative of that function, e to the power of fx. So in other words, that kind of remains the same when we differentiate it, right? And we can keep differentiating it. It will still remain the same. So those things remain the same. So therefore, it makes sense that our solution will also remain the same as well. That, this will also remain the same as that. Okay. And in actual fact, you could put a b in and see what happens. You should end up that b just equals 2, though. Okay, but like I say, this is a thing with differential equations. Sometimes you do have to guess, and you have to be kind of quite clever and sneaky about making a guess. And the more practice you get doing with them, the more kind of familiar and more comfortable with them you get. The more kind of the more your brain gets used to them, the more it kind of thinks, oh, I wonder if I try that, or I wonder if I try that. You kind of get from experience, you know what to put in. Yeah. But for the moment, the right-hand side is a pretty good guess of what it's going to look like. Okay. So basically, the first thing we need is we want to basically say, well, this satisfies this. So basically, we need that function, which is fine, we've got it. We also need the derivatives as well. So we need the first derivative and second derivative. So let's take the first derivative. The first derivative of that is going to be 2a e to the 2t, right? And the second derivative of that is going to be 4a e to the 2t, because it's going to be 2 times this thing up here. Okay, that's just a derivative of an exponential function. Okay, so next step then, because it'd be really nice to know what this a is. So next step then is to kind of put it into this equation, because if it does satisfy it, then it should satisfy this equation. Okay, so let's put it into this equation. So in other words, we get, so let's just put it in. So let's replace that with that y here. So in other words, it's going to be a e to the 2t. Okay, let's replace that y dash with that thing there. So y dash is going to be 3 times 2a e to the 2t. Okay, and then let's replace y double dash with that thing there. So 4a e to the 2t. So I've just plugged all those things in. Okay, let's do a little bit of simplifying then. So we end up with 4a e to the 2t minus 6a e to the 2t minus 4a e to the 2t equals 3 e to the 2t. Well, notice I've got an e to the 2t there, e to the 2t there, and an e to the 2t there. I'm just going to divide through by e to the 2t, or maybe if you want to see it like this, I'm going to take out e to the 2t. I'm going to take out e to the 2t. So let's stick an e to the 2t here, okay, and then I can basically factor it out, okay, in there, and then I'm just going to divide through by e to the 2t, because I've got an e to the 2t over here and e to the 2t here, so I'm just going to divide through. So we end up with that. Let's do a simplification of that. So we end up with 4a minus 4a is going to be 0a, okay, minus 6a, and that's going to be equal to the right-hand side, which is 3, okay. So in other words, then I can basically say that a equals minus 3 over 2, which is minus a half. Okay, so a equals minus a half. What was my original solution that I was looking for? There's my original solution. So I found a particular solution. So my original solution was y equals a e to the 2t. Okay, if I just replace a with a minus the half, then therefore that is my particular solution which I found. In actual fact, you can verify yourself that when you plug this particular solution back into here, the left-hand side does in fact equal the right-hand side. So when we plug yp equals minus a half e to the 2t, the left-hand side, so, when we plug it into here, we get the left-hand side equals the right-hand side. So therefore, we found a particular solution. So then what's our general solution? Well, our general solution is going to be yc, so our general solution y is going to be, a general solution to the non-homogeneous equation is going to be yc, which is c1 e to the 4t, plus c2 e to the minus t. We found that earlier, it's just that thing there. Okay, plus my particular solution, which I've just found. So minus a half e to the 2t, or plus minus a half, which of course becomes minus a half e to the 2t. Okay, and actually you can verify that if you plug this back into there, then you can actually find then it will satisfy it. It will satisfy it for certain constants C1 and C2. Okay? And you may say, well, how do you know C1 and C2? You can find C1 and C2 just by making, if you get given some initial conditions, for example, you can find what C1 and C2 are. I mean, I've seen kind of examples of initial value problems, for example. So in other words, you get given some initial conditions to find what C1 and C2 are. That's not really too much of an issue. But basically what I'm saying here is that my general solution is that if I put that in there, then I get exactly what I want. Okay? Then, it will satisfy it. Left-hand side equals right-hand side. So basically what the idea is that when you see an exponential right-hand side, you try something of this form. Okay? That kind of makes sense.